Hey everyone, and welcome. Today, we are going to dive right into the high-stakes, real-world puzzle of how products actually move around the globe. We're jumping straight into this explainer on supply chain optimization. From a massive manufacturing shipment crossing oceans, all the way down to a single tiny package landing right on your doorstep, there is this entire hidden universe of complex math and, frankly, unpredictable human behavior that makes it all happen. So today, we're unpacking some truly fascinating source material with case studies from Europe, North America, and India. It's going to be a fun ride.
Okay, let's dive into this. Here is our roadmap for today. First, we'll look at the supply chain puzzle as a whole. Then we go macro with network design, jump down to the meso level for Amazon's trailer Tetris, get incredibly micro with India's last mile, and finally wrap it up with the optimization mindset.
All right, kicking things off with Section 1, the supply chain puzzle.
I really want you to think about this question for a second. When you're sitting on your couch and you click buy on your phone, how does that physical item actually make it to your front door? I mean, we totally take it for granted, right? But behind that one simple click is a massive, highly constrained mathematical problem. Literally every single step of the journey involves balancing costs, strict time limits, the physical capacity of vehicles, and, as we'll see, the totally unpredictable nature of human beings.
Now officially, according to guidelines from the USAID Deliver Project, supply chain optimization is defined as a quantitative, commercial sector approach. It uses simulation and routine data to design flexible strategies that increase performance and cost effectiveness. Okay, I know that sounds super dry and academic, but actually, it's anything but. This is a vital, dynamic tool used to answer critical questions, like how many warehouses do we actually need? What specific types of trucks should we buy? What happens to our business if there's a sudden massive shock to the global system? What we do is use optimization models to essentially build a digital twin of a supply chain. It's like a sandbox where we can test out endless scenarios before a company spends a single dime in the real world.
But to build these digital models, we need the right ingredients. Optimization modeling brings together three core pieces of data. First, sites. Literally, where are the factories and warehouses located on a map? Second, products. What are we moving? What's the volume? How heavy is it? And third, demand. How much of this stuff do customers actually want, and exactly when do they need it? By funneling all this data into advanced simulation software, companies can spot hidden redundancies and figure out exactly what needs to change to make things run smoother.
Moving right along, let's zoom out to our first case study, Section 2, Macro Network Design.
Now, what's really interesting about this slide is the clash between human gut instinct and mathematical reality. We're looking at a global packaging company operating in France. Currently, this company uses a single warehouse strategy for the entire country. But their sales group had an idea. They thought, hey, what if we split things up? They proposed moving to a two-warehouse system, putting one facility in the east and one in the west. Their assumption was that by being physically closer to the customers, they would naturally optimize their transportation costs and guarantee faster on-time deliveries. I mean, it makes total logical sense, right? You add more warehouses, you get shorter trips, you save money.
But then, they ran the optimization algorithm. And wow. The model calculated that switching to the two-warehouse system would actually result in a cost increase of exactly 75,437 euros and 28 cents per month. That is a massive spike. It completely shatters the assumption that simply adding facilities automatically cuts your costs.
So what on earth went wrong here? Well, the model revealed that by splitting their inventory across two separate warehouses, the company no longer had enough sheer volume going to either location to fill up their highly efficient ship and train containers. And to make matters more complicated, the company had a strict security constraint. To prevent massive delays in case of an accident, they capped train and ship usage at a maximum of 80% of any given delivery. Because they couldn't hit full capacity on the cheaper rail and sea options, the math showed they would be forced to rely way more heavily on much more expensive truck transportation to make up the difference. The algorithm literally saved this company from making a 75,000 euro monthly mistake.
All right, let's step inside the warehouse for Section 3, Meso-level operations. We're going to look at Amazon's trailer Tetris.
Here's the thing. Having the perfect macro network across a whole country doesn't mean much if the operations inside your actual facilities are a total mess. When you're moving products between massive distribution centers, you have a choice to make. The traditional method uses palletized trailers, meaning everything sits nicely on those standard wooden pallets you've probably seen. But wooden pallets take up valuable space. So to maximize efficiency, Amazon has been transitioning heavily to what are called floor loads. It is literally trailer Tetris. You stack cardboard cases and plastic totes directly onto the floor of the trailer, totally eliminating the empty gaps and ditching the wooden pallets entirely. You can fit way more stuff in the truck this way. They even use hybrid floor loads, mixing standard totes and odd-sized cardboard cases together to maximize absolutely every square inch of air inside that truck.
Let's move to the next step and see how this builds, because this efficiency trick creates a massive operational headache when the truck arrives at its destination. In the newer Amazon robotics fulfillment centers, they use a process called decant. When a truck pulls up to the dock, any product that's still in a cardboard case has to be immediately removed from its original packaging and placed into one of those standard yellow plastic totes. They do this so that the automated robots inside the warehouse can process everything uniformly down the line.
But here is the catch. This perfectly optimized, jam-packed truckload causes a massive meso-level bottleneck. Because a hybrid floor load is essentially a chaotic, mixed-up game of Tetris, the warehouse workers unloading the trailer are dealing with a totally unpredictable flow of items. For 10 minutes, it might be all yellow totes, and then suddenly it's an avalanche of cardboard cases that all need to be decanted. This unpredictable variability means the decant line is frequently swinging between two extremes. It's either totally overwhelmed with too many boxes, or it's completely starved for work while guys stand around waiting. The labor becomes incredibly inefficient. It's such a great lesson. Hyper-optimizing for physical space inside the trailer can actually damage your workflow inside the building.
Okay, we've seen the national network, we've seen the warehouse stock. Let's zoom all the way down to the street. Section 4, Micro, India's last mile. If you're sitting there thinking that algorithmic route optimization can solve any delivery problem, well, the urban last mile in India is going to prove you wrong. Logistics companies there, like Delivery, operate in what researchers call a logistics black box. The environment features this incredible urban duality. You have modern, highly planned commercial areas right next to completely unplanned urban villages known as Lal Dora settlements. Inside these settlements, there are often zero street signs. Addresses aren't geospatial points on a grid, they're descriptive. Someone's address might literally be near the blue gate past the old temple. Add to that the fact that the Indian e-commerce market heavily relies on cash on delivery. Because of these immense physical and institutional hurdles, the aggregate first-attempt delivery failure rate in these areas is a staggering 23%. Standard Western-style routing algorithms, yeah, they completely break down here because the digital map simply does not match the messy reality on the ground. And this brilliantly illustrates that confusing geography isn't even the biggest problem here. Human friction plays a massive role. Look at this data. When an online order is prepaid, the return-to-origin rate, meaning the delivery failed and went back to the warehouse, is 6.2%. But when that exact same package is cash on delivery, the failure rate spikes to 20.4%. That is over 3 times higher. Why? Well, it's the human element. The delivery driver might not have exact change, or the customer might suddenly get buyer's remorse when forced to physically hand over hard cash. Or maybe the cash exchange just takes way too long and throws off the driver's schedule. Human behavioral friction ruins the last-mile delivery just as much as an unmapped street does.
Which brings us to our final takeaway. Section 5, the optimization mindset.
So what does all of this mean for how we actually think about supply chains? As we've just seen, pure math eventually hits a wall when it comes up against human variability. To truly succeed in these complex environments, there has to be a total paradigm shift. Like the Indian logistics research points out, we have to replace pure route optimization with what they call interaction optimization. Basically, the customer can no longer just be a passive dot on a map waiting for a package, they have to actively contribute to the process. Maybe that means they drop a WhatsApp pin for the driver or jump on a quick phone call to guide them through that final 50 meters. True optimization isn't just crunching numbers. It requires a brilliant blend of heavy mathematical modeling and human-centric, hyper-localized design.
I want to leave you with this provocative thought as we wrap up this explainer. Algorithms can calculate the absolute most cost-effective way to move a massive shipping container from one side of the globe to the other with incredible precision, but they still totally fail to navigate the final unmapped street or figure out what to do with a customer who doesn't have exact change. The supply chain puzzle, no matter how advanced our tech gets, will always require human intelligence to complete. Thank you so much for joining me to explore this. Keep wondering how things get to your door, and I'll catch you in the next one.